especially since the screen's working. So 5.8 exponential growth and decay, we have 3 different functions, one for exponential growth, and there are 2 versions of it. We have p, a to the x, where p is the principal, and a is the growth factor, and x is the time period. And if you're given like that the population doubles or triples, anything bigger than 1 would go in for your growth factor. So that's the function we use if we're given the growth factor. And if you're given a percentage, then here R would represent your percentage of growth. So if we were growing by 14%, we would change that value to a real number, 0.14, and my growth rate would then be 1.14. So that's the formula you use if you're given a percentage for a growth rate. And then exponential decay, we have a decay factor. That's when a is between 0 and 1, when it's a fraction. X is still the time period, and p is the starting amount or principal factor. And then my radioactive decay is if I have something that has a certain shelf life. Every, say, 8 days it's cut in half. So if you start with 10 grams of substance, after 8 days it would be down to 5 grams, and after 16 days it would be down to 2.5 grams, and so forth. So that's radioactive decay. So we're going to see an example of each one of those functions. So the first one, we're using the very left equation because we're given that the fruit fly population triples every day, so we know our growth factor is 3. We know our starting amount of fruit flies. Try and get this to work. Well, let's try that again. I have a sound bite here. How do we make it stop? Fruit fly population, you feel like you're getting, there it goes. So there, we start with 200, and then they triple every day. That's kind of scary. How many fruit flies will there be in 7 days? So we have 200 times 3 to the 7th. So if you use your trusty calculator, you should get 437,000, oh boy, 400 fruit flies. So kind of scary. We're going to talk a little bit about the logistics equation and how that would be limited. Eventually, you'd have to hit an equilibrium state. They can't just keep growing in population. So that's using the exponential growth equation on the far left. Here's another one, number 2. Filtering tap water removes 30% each time. How many times would I have to filter to ensure that 95% of impurities were removed? So the fact that I'm removing each time puts me in the category of not growth, but decay. The fact that I'm not given a decay factor, I'm actually given a percentage, tells me to go ahead and use the one that I'm going to highlight here. Just because I want to use my highlighter. So there it is. So I would use that one because I'm given a percentage, right? I'm given a percentage of decay. So I'm going to use the P1 minus R to the X. So let's go ahead and, maybe we should write that down here because I can't see it now. So we have A equals P times 1 minus R to the X. So it's saying on this one that filtering tap water removes 30% each time. So 30% is my R. Let's underline that. And it says how many times would I have to filter to ensure that 95% of impurities were removed. So 95% of impurities were removed. A couple different ways to think about this. If A represents amount, and it's not that I'm looking to get to 95% or 0.95, it's that the only amount that should be left is 0.05. So if I think of it in terms of impurities still remaining, so impurities still remaining here, maybe write that down. Impurities still remaining, then I want to get the A down to what value? Basically 100% minus 95%, which equals 5%. You with me? So if I'm doing this in terms of impurities, then I'm looking to how many times am I going to have to filter until only 5% impurities remain? And it's going to be fine to drink probably. So plug in for A, 0.05. What is P going to be in this case? Yes. So we're going to start with P is going to be 100% would represent 1. It's 100%. And then I have 1 minus, now the R is the 30%, which is 0.30, and then to the X. So I have this exponential equation, and I happen to have a variable power. See if you can go ahead and solve that right now. See if you can solve that guy. What's going to happen when I put these two together? I might do that step with you. We can just drop the 1, but 1 minus 0.3 gives me 0.7, which is a value between 0 and 1, so that makes sense, right? It should be decaying here, going down. So do you know how to solve that using ln? Use ln to go ahead and solve that right now. So you should get about 9 times. You're going to have to do it 9 times. It ends up being a little less than that. But if x equals ln of the argument, 0.05, over ln of the base, 0.7, we get approximately 8.399. How come I have to, how come I'm rounding up here? I either do a filter cycle or we don't. I'm not going to be down at the 5% or less level of impurities unless I do a full 9 filter cycle. Okay. I have to do 9 cycles to get it there. It's one of those examples of problem where you kind of have to answer it in terms of the context of what it says. What is X represent? X represents the number of times I would have to filter to ensure that there's only 5% impurities left.
So we would round.
Yes. So we would say, yes, we would round that up. So we'd say, we must filter 9 times. So yeah, the 9 represents filter cycles. I don't really have a time period attached to X. I don't know how long a filter cycle takes, but it's 9 filter cycles. Right? Number 3. Number 3 is going to use my third equation over on the right. So number 3 is talking about radioactive decay. So we're going to use this formula right here. Okay? And I only gave you one version of this formula. Okay? Each of these has 2 versions, depending on if you're given a percent or if you're given the growth or decay factor. So here it says the half-life of carbon-14 is 5,730 years. Whew. How old is a mummy that lost 40% of its carbon-14? So if the mummy lost 40% of its carbon-14, then what remains A is equal to 100% minus 40% or 60%. So that's going to give me my A, the amount. And so my equation is, it might help to write down my equation because I can't see it here. So you have A equals, it's P 0.5 to the X over H. So it's P 0.5 to the X over H power. So here we go. The amount is 0.6. The starting amount, kind of like the last problem, we started at, we don't know what the actual amount is, we're just going to call it 100%, so we'll put a 1 in for P. 1 represents 100%. 0.5 to the X over H. So the X is the number of these cycles that has to happen. The H is the time period it takes to do a cycle. In this case, it's 5,730 years. 5,730 years. So all of that, the X over 5,730 is the power on the 0.5. Okay, the power on the 0.5. So let's go ahead and solve this one together. We would take ln of each side, so ln of 0.6 equals bring the power down. It's going to be x over 5730 ln of 0.5. Okay, so when I take ln of each side, it brings that down in front. And then I think we can take care of solving for x with these next two steps here, all in one step. So we're going to divide each side by ln of 0.5. So it's ln of 0.6 divided by ln of 0.5. And then we're also going to multiply by 5,730. And that will give us x. So ln of 0.6 divided by ln of 0.5 multiplied by 5,730. You should get right around the Egyptian Empire time here, 4,228 or 222.8 years old. So x should be, we'll use squiggly equals, about 4,222.8 years old. So we've used each equation, except for the growth equation on the right-hand side. Yeah. So, okay, so here we go. It says the population of Mexico was 67.4 million in 1980 and has increased approximately 2.6% yearly. So this one is, once again, let's go up here. I'm going to take my little highlight here. It's exponential growth again, but it's the one on the right this time. Okay, you know why? I've given a percent and not the growth factor. So I have amount equals starting amount 1 plus r to the x. And so it says estimate the population in 2020. We're going to assume that x equals 0 corresponds to 1980. So in this case, my amount, my estimate, is going to be equal to the starting amount in millions, 67.4, times 1 plus, I've got to change my rate to a real number. So be careful here. This is my r, and r is equal to 0.026, not 0.26. That'll give you problems here. To the power of what? 40, yes. 2020 minus 1980 gives me 40, and that's my power on that. So we'll use squiggly equals. My estimate for the population of Mexico then, based on this model, if it keeps growing exponentially, is going to be 188.2 million. We haven't gotten there yet to 2020, but I'll do my estimate. That's a lot of growth. All right, so any questions on any of those? Using the different formulas. The only one we did use is the left-hand side of the exponential decay one, but that's kind of like the radioactive decay. And I'm just telling you on the radioactive decay thought that the growth rate is, or the decay rate is 50%. It cuts in half each time. All right. Logistic model. We've talked a little bit about this, right? That it's not realistic to have exponential growth without any kind of bound, upper bound, right? So the logistic model is a way of taking care of that. The P of T is the P of T here. We've got the population. So this is population here. The C up here is the what we call the equilibrium state, or the limiting value, the carrying capacity. Lots of different names for the same thing, but carrying capacity, or the limiting value, limit, or we also have called it the horizontal asymptote. Remember in the Rumors Unleashed, that was the horizontal asymptote. of the function, but carrying capacity, limit, horizontal asymptote. And then B is the growth rate here. And T is the time. And then A is related to the initial amount. It's not exactly the initial amount, but it's related to it. So it says here, after environmentalists moved 6 endangered bald eagles to a controlled environment, the population grows according to the model P of T equals 500 over 1 plus 82.33 e to the negative 0.162 t, where t is in years. So what is the carrying capacity of the environment here? We can answer that just looking at the equation. Here it is. Carrying capacity is 500 eagles. So 500 eagles. What is the growth rate of the bald eagles? That we can pull right out of the equation. Can you change it to a percentage? Or?
Yeah, 16.2.
Yeah, there it is right there. 16.2%. So moving the decimal over. What is the population after 3 years? What is the population after 3 years? Yeah, I put 3 in there. So we might want to show how that is done on the calculator. Go ahead and pull out your calculator. Actually, I think we did this before, right? 500 over. Be sure to put parentheses around the bottom if you're in the classic mode here. 1 plus 82.33 e to the, also you'll have to put parentheses around the power as well. Negative 0.162, and then we're going to put in 3. So you will have to, on the classic mode, you'll have parentheses around the whole thing you're dividing by, and then also parentheses around the whole power that you're taking e to. So go ahead and plug that into your calculator. You should get approximately 10 eagles. So maybe check and make sure you can do that. Check and make sure you do that. I'm going to pull up my calculator. We'll graph this. We can kind of check it by graphing it. All right, so we're going to, I'm going to clear out all this. Make sure all your statistical plots are out. And when we graph it, we'll also be able to see about what the population was after 3 years. So here's my Windows. Well, let's go ahead and type it in first. So once again, if you're in classic mode, you have to do lots of parentheses here. I think I am in math type mode right now. We'll see in just a minute. I have 500 divided by, okay, I'm in classic. I can show you what it looks like. 1 plus 82.33, and then we hit second, and then the e to the x is right above ln. I'm in math mode here. And then I have negative 0.162, and then in parentheses I'm going to place the 3, and then I'm going to come down off of my exponent. There's another parentheses. So that's what it should look like when I, oh, sorry, I don't actually want the 3 there. I need to put x in there. We're going to graph it. We're not evaluating it. Okay. So make sure there's an x there. We can kind of use our trace function or our value function to find what the value is at 3. So here's what I suggest for a window once you plug that in. Window should go from 0 to 50. The scale, you might want to change the scale to 5s. And then the y-min, maybe go negative 500 to positive 500. And we can make a scale of perhaps 100. So here's my window suggestion, and then we'll graph it and answer the last 2 questions on that. So x-min 0, x-max 50, x scale 5. Y-min negative 500, Y-max 500, Y scale 100, and hit graph. You can see at 1, 2, about 3, I'm up near. If you go to second, calculate value and type in 3, it will give you the value of about 9.68 or about 10. And then if I want to find out when the population will, when will the population be 300, we could type in value again. So second, calculate value. Actually, in this case, we're still correct. So when will the population be 300? One way to do this would go to y equals and put in 300 as your second graph, and then find the intersection. So if you plug in 300 as your second graph, or you can set it equal to 0 and solve. But if I go to number 5, intersect, it will find exactly what is the value of t when it's 300. First curve, second curve, guess. About 29.7. So it's probably helpful just to put in another graph, y equals 300. So 29.7 years is when the population will reach 300. And then if you wanted to switch this up to answer the last question, how long will it take for the population to reach half of the carrying capacity? What is half of the carrying capacity? So you could go back here and change your 300 to a 250 instead, and do the same process. So we hit graph, it'll graph each of those. Here's my logistics equation. It's graphing very slowly. I'm going to graph my line y equals 250 pretty quickly. Now I'm just finding the intersection between my logistics graph and the line y equals 250. You can just hit first curve, second curve, guess, just boom, 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 because there's only 2 curves on there. And you get 27.2. So the first one, part D, was 29.7 years. E was 27.2. So very quickly we reached half of the carrying capacity, right? Quickly. Well, actually not quickly, but what I'm saying is there's not a big difference between when you reach half the carrying capacity up to 300. It's relatively quickly. And then it's going to slow down after that. So 29.7 and 27.2. 29.7. 27.2 years.